upstairs. It's always too cold. All right. So this strange looking orbital diagram set of boxes is a scheme that we have set up that shows energy for the electrons. Low energy is down at the bottom, high energy is up at the top. We have boxes that represent orbitals. We have numbers that represent energy levels, and we have letters that represent energy sublevels. Okay, so what I just say, did you write any of that down? See, one thing that happens is a lot of people they write down what I write down, and they're not really listening, they're just looking. So what did I just say? Placement on the page. I told you that the electron energy level was something. Something up. Are the letters S, P, D, and F. The electron orbitals are the boxes, and electrons themselves are arrows. So an orbital diagram gives electron information. And this electron information is what we're going to need for us to understand what happens for an atom to become more stable and form chemical bonds with other atoms. So the parts of an orbital, the placement on the page shows energy. The specific energy is given by a number, the principal quantum number. And you see the 1s, the 2s, the 3s, the 6s, and so on. The energy sublevels within an energy level are designated S, P, D, and F, and that's in terms of their energy, S being the lowest energy sublevel and F being the highest. The orbitals that can actually represent where you'll probably find an electron, those orbitals, those statistical probability zones, we just make a box, and we're going to put arrows in the boxes. Element is O. Oxygen. And I want you right now in another tab to open ptable.com. And while you're there, find out how many electrons oxygen has. So I need to make 8 arrows to show where each is. There's some fundamental rules, and one of them is electrons fill the lowest energy level first. The lowest energy level would be the first energy level. So I'm going to come over here, and I'm going to put an electron in there. I need to get a little, there we go. And so I just put an electron in there. I just make a half arrow. I could make it a whole arrow. It's just kind of hard to fit it all in the little box. Are you with me so far? I'm at the first energy level, the S sublevel, and I see one orbital. That's what I call a box. And I put one of the 8 electrons in there. Now, an orbital can hold 2 electrons, so I'm going to put the second one in there. And I just show the arrow pointing in the opposite direction to imply the 4th quantum number, which represents the spin to create opposing magnetic fields to let them share that orbital space. But I'm supposed to put 8 in there, and I've only put 2, so I need to keep going. So I'm going to move up, and when I get to the next box, I've hit the second energy level, the S sublevel, and I'm going to put 2 electrons in there. And I've accounted for 4 of my 8. But that orbital is now full, so I need to go up till I find the next box. And then I hit 3 boxes that are exactly alike. Which one shall I put an electron in? It really doesn't matter. I usually just do the first one first. And now I need to put, I've got 5 electrons. Where does electron number 6 go? This does matter because each of these are equal energy orbitals. And so when I put my next electron here, I'm going to put it in the next available orbital. I think I mentioned before, if you share a room, you can't wait till that person leaves for college, or you can't wait to get out of there, because if there was an empty room, one of you would move into it. That's exactly the same thing with electrons. The electrons have that electrostatic repulsion, and so if there are multiple equal energy orbitals, they're often referred to as degenerate orbitals. So if you're watching a video or reading something and you see that word, it doesn't mean that they're beyond redemption. It just means that they have equal energy. So I have 2, 4, 6 of my 8 electrons in a position. Electron number 7 goes here. And now we're going to be forced to share orbitals. So I go back to my first orbital and place electron number 8. So I show 2, 4, 6, 7, 8 electrons. What's significant here is that this shows that we have the first energy level is filled. The second energy level is filled. And in the 2p sublevel, 1 orbital is filled and 2 are half full. That's important. This points out that oxygen has 2 unpaired electrons, and that's why oxygen acts the way it does in chemical bonds. Those 2 electrons are right there, are the whole reason we're drawing these orbital diagrams, because we can predict what oxygen's going to chemically react with. We can see, hey, if we got 2 more electrons for that oxygen, it would have the whole second energy level filled too. And that is a stable arrangement. Having a filled energy level is a significant thing. Having a filled sublevel is an important balance situation in terms of electrostatic charge in relation to the nucleus, between the negative electrons and the positive protons in the nucleus and the electrons out there in these orbitals. And having just 2 more to complete a whole sublevel is an important set of circumstances. That's what influences the chemical behavior of oxygen. And when we do this for all the other elements, that set of circumstances that you see out there in the outermost energy level, known as the valence energy level, we filled the first energy level. We have not filled the second energy level. We refer to all the filled energy level as the core electrons, and we refer to the outermost energy level as the valence electrons. The lower filled energy levels are known as the core electrons. The electrons found in the outermost unfilled level or energy level are known as the valence electrons. Configuration for oxygen says, hey, in the first energy level down here, in the first energy level, the S sublevel, that orbital has 2 electrons in it. We move up to the next energy level, the second energy level. We first encounter the S sublevel, and in my box, I have 2 electrons in it. I go up to the next energy sublevel. It's in the second energy level. It's in the P sublevel. And I have 1, 2, 3, 4 electrons in it. That's 4. What's 4 plus 4? 8. The superscript, the little exponents, are the number of electrons. And you know that oxygen has 8 electrons. So this electron configuration for oxygen shows the energy levels with the numbers. Energy sublevels. Orbitals don't show up in an electron configuration. We don't have any way of indicating the boxes. We just do a total electron count